Okay, so I'm Miles. I'm going to be talking about multi-threading in games. Just because, originally I wasn't sure how to approach this talk. I know I want to talk about Rust, and I could talk for ages about like how good Rust is for multi-threading. But I wasn't really sure the technical level. If you're all like multi-threading experts, this will be a little low level. I know there's a variety of people who come to these, so I wanted to keep things pretty intuitive and understandable. I'm not going to be talking about, I'm not going to be showing you any numbers or really getting into any specific algorithms or too much code. So hopefully it's approachable, and if you want to talk about more like specific technical stuff, come and find me afterward. Multi-threading, can I get a show of hands? Like, people know what that term is, right? Okay, everyone's roughly familiar. You've got multiple cores in your computer. Normally a single core can execute a single set of instructions, a single sequence of instructions. But now we have multiple cores, so you can execute multiple sequences of instructions at the same time. If you're solving a problem that can be easily split up into multiple little sub-problems, then you can run multiple versions of that program on different parts of your problem and solve it faster. If you have 8 cores, and it's like a perfectly embarrassingly parallel program, then you can get an 8 times speed up, maybe. Usually it's a little less than that. There we go. The other thing I want to mention before we get into it is I'm going to be describing this in the context of games, but really we're talking about real-time apps, real-time applications. Those are things that are generally rendering stuff you're trying to hit 60 FPS. There's lots of stuff that aren't games that are like this, where you're just doing a bunch of stuff and you have to present stuff to the users all the time. So like artist apps fall into this category. Engineering apps, that's what I do at work. We use Bevy, which we'll talk about in a second, to make CAD engineering apps. Also sometimes compilers, things that just need to give feedback as quickly as possible or feel interactive. These are all real-time apps. And so the stuff I'm talking about here is hopefully going to be broadly applicable to that, and we're going to be talking about just sort of the theory about how to approach using multi-threading to make these hit performance targets. As I mentioned before, I use Bevy at work. Bevy is a Rust game engine that some of you may have heard of. There's some people in Bevy shirts here. Bevy is a game engine primarily, and one of the interesting things about Bevy is that it is highly parallel, more than most game engines. Part of why that's possible is because Rust makes multi-threading really easy. It's really easy to do multi-threading in a safe, reliable way because of all of the language features. There's some story that Mozilla used to have like a sign up in the office that was like, you must be this tall to do multi-threading by hand. Like it's an extremely difficult thing to do, and I think one of the amazing things about Rust is how much more reliable and safe highly multi-threaded, highly parallel, low-level programs can be. And that's why Bevy uses Rust. That's one of the big reasons. So before I get into the meat of the talk, I want to talk about the idea of tasks a little bit. So this is a frame from a game called Tiny Glade, which is built partially using Bevy. It doesn't use all of Bevy, but it does use the task system, which is why I'm okay showing this. So imagine you're rendering this frame. You're trying to render these, at 60 FPS, so you have 16 milliseconds or whatever to render these. You can imagine all of the work that goes into rendering that frame as a list of tasks that you have to execute. Not all of them have to be executed in a specific order. For instance, if you're moving your camera around, you may be having to determine what models are in view of the camera so that you don't send stuff that isn't within the camera frustum to your GPU. Here, we're like clicking on a little sheep. There's a whole UI interaction. All of that you could describe as tasks. What is a task? What goes into a task? That's totally arbitrary, right? You could think of like rendering as a task, and UI is a task, and game logic is a task, and you have 3 tasks. And maybe they're separate, you can execute them on 3 separate threads because you can run them in any order. Or you can be much more granular. You could say, I can describe every single model here, every single texture as a task. Maybe if you're loading assets, that could be a task. These are all, just be thinking about tasks as like little increments of work that you need to complete. The reason I'm talking about this, and the meat of this talk, is that that currently multi-threading games and multi-threading real-time applications is still a little difficult. And so I've written a crate, which is designed to make it a little easier to get good performance on these sorts of applications. And we're going to be talking about the design of that crate a little bit and what informs the design choices there. I would describe this crate is called Forte. I would describe it as a low latency parallel work scheduler. So work scheduler means it allows you to execute concurrent programs. Concurrent programs are programs that are described in such a way that they can be executed in multiple different orders or distributed over multiple threads and executed in parallel. Those programs can't really just run on a computer. They have to be scheduled. You have to pick what runs where, what threads you run different things on, when you run different tasks. So this is the part of that application. It just runs those tasks on threads. It is parallel, so it can run them on multiple threads at the same time, and it's low latency. We'll talk about latency and throughput in a little bit, but it means it prioritizes execution speed. It's a little bit of a cop-out describing it that way. This is necessary because getting good multi-threaded performance is still hard. Rust has made it really easy to use multi-threading, but getting performance is non-trivial. You can't always just walk in and add some threads and speed your problem up. And especially if you have these really tight latency requirements that you tend to see. So I'll talk about these issues in depth here, but these are the main 4 things that at Bevy we've identified as being sort of problems that need to be addressed that lead to bad multi-threaded performance. I got interested in this because Bevy has 2 ways of executing stuff. It has like a single-threaded mode and a parallel mode. And recently we did some profiling, like more than a year ago, and we were like, oh no, the multi-threaded mode is almost always slower than the single-threaded mode. That's bad. So we've been looking at a bunch of different ways. There's no easy solution to that, but this is one aspect of how we are approaching fixing that, so the multi-threaded solution is actually faster. The biggest characteristic of real-time applications is that they care about absolute frame times. So if you're rendering at 60 FPS, you have to render things in 16 milliseconds. Just as an example, you imagine you have some tasks. Let's say you have 50,000 tasks, which is a lot of tasks, but not like a crazy number of tasks. And you have some small overhead, like 50 nanoseconds. That's like maybe unlocking a mutex a couple times, locking a mutex, maybe if it's contested. It's not a huge overhead. If you do the math here, then if you're rendering at 60 FPS, you will have to be spending 15% of your time on just that overhead. If that's single-threaded, then you're spending 15% of your frame just doing nothing but figuring out where to run work. That's an easy way to lose a lot of performance. Games, in particular, also tend to be highly iterative and hard to parallelize because of that. So imagine part of a game might be a physics engine. The typical way to write a physics engine is to have a bunch of steps. First, you need to find the collisions, and then you need to move objects apart and update forces. And actually, to get stability there, you need to do that 3 or 4 times. And then each part of that, for instance, a collision solver, which is just one part of that sequence of steps, may have 12 or more sub-steps where you're like doing graph coloring, and so each of those steps has to happen sequentially, but you want them to happen as fast as possible, and each of the sub-steps is embarrassingly parallel. So you want to go as wide as possible in as short a time as possible, repeatedly. Just a graph coloring collision system can add like 50 iterations of the same parallel operation, which means any overhead on that is multiplied by 50. So it's an important case to optimize. I'm talking about latency here, so we should define that. Latency is I didn't make this graph. Latency is a measure of the absolute time it takes to complete a task. And throughput is a measure of the number of tasks you can complete at once. There is a relationship between latency and throughput that will be very important, so it's good to understand this. They both tend to increase together. And when you reach your peak throughput, where your hardware is saturated, you're running everything you can on all of your CPUs, latency spikes because you have to queue stuff. When you have available hardware, your latency tends to be lower. In general, for these types of schedulers, you optimize for one of these 2 cases. Either the case where your hardware is underutilized, or the case where it is overutilized, where you were queuing stuff. If you care about latency, you want to have available hardware so that you can start executing things immediately. If you care about throughput, you always want to have back pressure. You always want to be able to pull new tasks off of the queue. And so when you're writing a scheduler, you have a choice. Do you optimize for the case where things are underutilized? Are you latency forward? Or do you optimize for the case where things are queued? Are you throughput oriented? As we'll see later, this choice matters a lot. Rayon, for instance, is highly throughput optimized, and that's part of the reason that Bevy does not use Rayon, even though it's an excellent library. Speaking of this sort of split, there's another bifurcation in the Rust ecosystem, which is that there's async, right? We have futures. Raise your hand if you used futures in Rust or Rust async. That's most people you're familiar with. The people who have it, have you seen it and been like, I'm not doing that? There's a really big split between futures and non-futures because of function coloring, but they're also used for different things. So IO-bound work is better for async usually. It lets you like go to sleep until you receive some message. So if you're doing like a lot of file system stuff, a lot of networking, typically you're going to use something like Tokyo if you want it to be multi-threaded. Or there's also single-threaded versions which do async. If your work is CPU-bound, which like plain old Rust is usually CPU-bound if you're doing just computations, and you want to multi-thread that, there's a great solution for it, which is Rayon, which Nico wrote. Most programs, a lot of programs fit neatly into one of these two columns. If you're doing like statistics or data science, that's going to be compute bound, right? You're crunching a lot of numbers, you use Rayon. If you're doing like a web hosting thing, you're probably going to use Tokyo. Games are in an awkward position because they need both. With games, you're often loading assets from a file system, you're communicating with the game server, you're also having to do things like frustum culling or physics. Those are number crunching. So you need both really good async support and like CPU-bound stuff. And that doesn't really exist in the ecosystem. You can use you can try and combine the gold standard for using for these individual things. Like you can try and combine Rayon and Tokyo, but you only have so many cores. If you load up a Tokyo thread pool and you load up a Rayon thread pool at the same time, they're going to fight each other. And we've measured it at my work. It tends to be slower. Another aspect, this is a bit more subtle, is that games and commercial software, you're selling software, people are going to run it on their devices. So you don't know what it's running on. You're not running this in like a data center or whatever. A lot of existing schedulers, especially the C++ ones, are built around the idea of tuning. So you're going to take your workload, and there was that question like, how do we know what goes into a task? Well, at this step, you just sort of guess and check. You assemble things into tasks at a certain granularity, and then you compile it, and you see what the performance is, and then you try a different one, and you pick whatever is better on your machine. This works great for a supercomputer. It is less good when you are deploying to potentially phones or MacBooks or arbitrary computers people build themselves. And this is not an academic problem, because the more machines your game or software can run effectively on, the more machines you can hit performance targets on, the more sales you can get, the more people you can sell stuff to. Throughput focused schedulers like Rayon don't tend to care about this as much, and I can talk about why that is later. And then the last thing to talk about is that many existing solutions, even in the Rust ecosystem, have pretty high CPU usage. People notice when their fan turns on. They notice when their battery starts dropping and they're not doing anything. So if you have high background CPU usage, it's going to affect thermals, and people will complain about it. This is the other reason why Bevy doesn't use Rayon. Bevy, the game engine, used to use Rayon, which is this parallelism library. The CPU usage was too high. We eventually switched off because of that. So based on these problems, we can sort of assemble a wish list. Like if we are making, say theoretically, you're making a game engine in Rust, you need a scheduler for it. This is what we would want. We would want it to support async and blocking work. We would want it to be latency oriented. We would want it to avoid compile time workload tuning, and we would want to minimize CPU utilization. Luckily, the first one at least is pretty trivial to add to Rayon. the Rayon devs have had a plan for adding a bunch of async stuff. They actually have full code examples and like really thought everything through. They've had a plan to add stuff to Rayon for ages, and the main reason it seems to not have been done is because Rayon is throughput oriented, and most async runtimes are latency oriented, and it doesn't usually make sense. But for us, it's really important. Looking at the other problems here, you can be like, well, we can solve one of these by just modifying Rayon. So that's what I have been doing. To attempt to address this problem with Bevy's latency, I've been trying to hack what I need into Rayon. And that's what Forte is. It's similar to Rayon. I would describe it as a close cousin. The structures are similar. It's not a fork. No actual code is shared, basically, except like the thread safety exception handling stuff. All of the other three issues here, and this is going to be a bit of a controversial point, but for the purposes of this talk, all of the other issues here are tied to a choice that Rayon makes that is really common with scheduling. It's how most like multi-threaded apps work, which is work stealing. Has anyone heard of work stealing? Okay, every time a little fewer. We're going to talk about what it is. Work stealing is, I have to preface this, the gold standard for how you balance work between threads. It is so common that it is almost synonymous with like load balancing of tasks on a thread pool. This is how you do it. There's two bits in it. The first, most work stealing stuff is based on eager binary splitting. So let's say you have some slice. You're going to have to deal with these illustrations. The rest of this talk is these illustrations. Imagine you have some slice, some arbitrary slice, and you want to parallelize over it. If you've used Rayon and you hit .pariter or whatever, this is what's going on under the hood. The first thing that it's going to do is turn this slice into tasks that it can execute. So it's eager binary splitting. That should tell you about how it does that a little bit. We're going to take the slice and we're going to cut it in half, and we're going to put half of it in one task and half in the other. And then we're going to put them both on a stack. Well, we've done that, so we need to execute something. So we pull something off the stack, and we open it up, and no, it's a slice. And we do the same thing again. We split it in half, so we get now two tasks that each have 2 items, and a third that has 4. And then we put those on a stack, and then we pull the last thing off, and we open it up, and we're like, okay, we can split this again. So we split it again, and we get 2 items, and then we put them on the stack, and then we're out of work, so we pull something off the stack to do, and we look at it, and we're like, we can't split this, so we execute it. This is a lot of work for executing stuff. Why do we do this? It's already seeming like a little bit of overhead. The reason we do this is the actual work stealing part. So these are processors. We've got 3 processors, A, B, and C. Each one of these has a stack that they are pushing and popping work to. The little red squares represent tasks. A is doing fine. It's doing its work. It doesn't have a ton of backlog. B has a ton of tasks in its stack. And C is out of work. It's finished its work early for some reason. Maybe it got sent less stuff. Maybe the tasks had less in them. So it turns into a pirate, and it goes over and it takes the oldest task from B, and it takes that and it puts it on its queue and it starts executing it. Now, in the previous thing we saw, we're getting smaller and smaller tasks. If we store them in the order that we create them, the oldest task is going to have half the work, and then the next tasks are going to have are going to have a quarter, and then an eighth, and so on. It gets smaller as you get down the stack. So if you're stealing from the top, you are going to steal half the work in just a single go, and then theoretically C will have all of the work that it needs to do. This is a great algorithm. It works really well. There are some issues with it for latency specifically. So one of the issues is, it's pretty as a diagram, but actually stealing takes a lot of work. This pirate has to stay alive even though it doesn't have any work. It could go to sleep, it could yield its time back to the operating system. It's going to choose not to. Instead, it's going to spin and check all of the other threads and try and pull work off of them. There are ways to prevent this from happening for too long. Eventually it can go to sleep, but already that's an issue because it will create contention on the other threads. If this thread is trying to interfere with the other thread's queue, they're going to sort of hit each other in a way that I don't want to get into. I'm not going to talk about atomics here. It will slow the system down. So they have to use sort of like a step back thing where it tries one and then it waits for some time and then it tries another and it waits for an exponential amount of time before eventually going to sleep. While it's doing that, it's spinning. It's just doing the same loop over and over again. And this is a massive source of CPU usage. This is why, to some extent, many parallel programs have pretty high CPU usage. If you can eliminate this spinning, it should theoretically have about the same CPU usage to a single-threaded version of the same thing, right? You're doing the same amount of work. That's a big issue with it. The other issue is the fact that you are, all of these queues, or stacks, or whatever you want to call them, the repositories where you're storing the tasks that you need to execute, those all need to be atomic. I'm not going to get into what that means, but it means that they can slow down randomly if other threads try to interact with them. They may have higher instruction costs, like it may require more instructions to implement them than a normal like list. Shoot. Oh no. Okay, I caught it before I did. Than a normal list, and it also limits the number of, not all algorithms can be implemented atomically. So like priority queues, which are very useful, you associate how high priority different tasks are, and you always take the highest priority one. Those are really hard to implement in an atomic system. You usually have to have multiple separate atomic queues, and then that has issues as well, increases memory use and stuff. So there is an alternative approach which has gotten some popularity recently. In fact, there's still work on improving this. There are a couple different small modifications. The one I want to talk about today is the one that Forte currently uses. There's another approach that I'm currently investigating, which I'm happy to talk about if we have time. But what I want to talk about is called heartbeat scheduling, which is very similar. It looks almost the same. There are a couple core differences here. The first difference is that when a specific CPU core runs out of work, it doesn't spin. When it runs out of work, it goes to sleep immediately. So already CPU usage should be significantly lower. This does mean that it has to be woken up if new work becomes available. But the other property of heartbeat scheduling is that new work only becomes available at fixed intervals. So what we've added here is a fourth core. And this core is in charge of scheduling and making sure that the other three cores don't conflict. Every so often, it has a little clock that's spinning around. Every so often, currently it's pointing at B, it gets to B, and this is an actual clock, so it's sleeping for 100 nanoseconds or something like that. It wakes up, the clock points to B, it says, B, okay, please share one of your tasks, if it has one. And so it does. And when B shares a task, it also wakes up a random worker, which in this case might be C. And then C is able to do that work. Then goes to sleep again and waits for a given amount of time, and then will wake up and say, C, please share some work. And at this point, there's two possibilities. C could already be done, in which case no work gets shared, or it could be, it could have split that work, and so it could have some work to contribute back to the pool. This has the effect that when the work is, when all the workers have work, they don't have to conflict with things that much. There isn't a rush to share a bunch of stuff. But it also means that all of this work can be done locally. So these queues, as opposed to being atomic, are fully local. This can be significantly faster, and it also allows us to implement things like priority queues and other things like that. But the most important property is that the amount of synchronization between any two cores is bounded by time. So you can get a really good estimate. You can mathematically guarantee that you will never have more overhead in a given amount of time. And that is controllable by the amount of time that it sleeps for. There are some issues with this. It relies on accurate timers, which people have used timers on Rust, timers on Windows maybe. They are not accurate. They are not accurate enough to have this work reliably. There are some ways around that. You can yield back, not for a specific amount of time, but for a time slice, and have the CPU just call you again when it feels like it. The performance of this is pretty good on some Toy benchmarks. So has anyone here heard of Chili? It was on Hacker News a little, yeah. I like that we're getting less. Good talk. So Chili is another implementation of this. This is partially based on the way Chili does things. There are some differences with Chili. We're going to get back to this crate. which is this supports an important subset of Rayon's API. They're pretty similar. There's a spawn function, which works for normal closures and for futures. There's a scoped spawn function, which works for things that are not static. There's a join method, which is one of the really big important things with Rayon. There's also things from async executors like block on. Currently, it does not support broadcast. It doesn't have different Rayon has like FIFO ordering and LIFO ordering. This is fixed. And so there's some stuff we're working on to get parity to Rayon. And that sort of brings us into current work. Originally, I had hoped to make this as identical to the Rayon core library as possible, and I did get there. So it was actually possible to run Rayon on top of Forte for a couple months. I do have benchmarks from that, which are favorable. It is generally slower than Rayon for super like throughput-oriented problems. But the CPU usage, especially for some of the unoptimized cases, is like an order of magnitude lower with not that much performance difference. However, I've had to make some changes to the API. It's still evolving, and so it's no longer possible to run it directly on top of Rayon. And also, there are some other approaches that I want to try that involve creating my own version of the Rayon top-level stuff. That's in development. The other thing that we're still working on is benchmarking and evaluation. I haven't gotten the opportunity to run this on a ton of hardware. I've run it on my Mac. I've run it on some Linux, Intel laptops. I've run it on an NVIDIA Tegra at this point. The Tegra has a deadlock that I can't identify on any other hardware. So like this is not production software. We're still trying this on new machines and encountering bugs on those machines and fixing them. And part of that is creating a more realistic benchmark suite. So I mentioned Chili. I think its benchmark is really stupid. I can get into why that is, but it's sort of something that it has created a problem and then solved. So this is faster on my MacBook than Chili for that problem, but I also don't think it's a super representative benchmark. I'm not going to talk about numbers because it is evolving so quickly. Thank you. But in general, for the comparisons against other like parallel schedulers in this class or against Rayon, I think the results are promising. I won't give any specific claims. The last thing we're working on is the Bevy integration. So this is currently not usable with Bevy. I haven't been able to talk a ton about how Bevy does multi-threading. If there's interest, I have an appendix with some information about that. So the big question will be whether or not this does alleviate some of that parallel overhead with Bevy. And that's the big benchmark that I'm going for. So currently, I'm working on a bunch of API changes and small tweaks that will make it easier to integrate into Bevy. Should just slot in and replace the current thing pretty much. That is the end of the talk. I think we have some extra time for questions, so thank you so much.